Good morning. We're gonna wait one more minute just for anybody else to come on. Okay, let's get started then. Um, so now, yesterday we talked about calculating speed and the difference between speed, velocity, distance, displacement. Now we're going to apply this onto a graph, basically. And there's another type of graph that I want to show you in another topic, but we're going to start off with this particular type of graph just as an introduction. And these types of graphs are called distance time graphs. But before any of that, let's take a step back and put our maths hats on. Physics is pretty much applied mathematics. So what I don't want is for you guys to think that physics and maths are two separate things, because they're not. Physics is mathematics put into a context of a real life scenario, basically. So when it comes to like certain words or graphing skills that you learn about in maths, the same can be applied in physics and science. So here's this word that you would have heard of in maths before called the gradient. Now, think back to maths. What does a gradient mean when we're talking about graphs? If during your maths lesson they ask you calculate the gradient of this line, what does that mean? Anyone type in the chat, tell me what gradient means. Okay, no takers, that's fine. So a gradient on a graph is basically like the slope. It's a measure of how steep the graph is. So think about it as like a measure of steepness. We call that the gradient. So if we had a bigger gradient, that means it's more steep. If we had a lesser gradient, like a lower gradient, that means it's less steep. And the gradient is pretty much just a number. Um, and the bigger that number, the more steep it is. The lower that number, the less steep it is. So in terms of calculating the gradient, I'm hoping that you would have heard of this formula before in maths, but basically it is rise over run. So how much it went up by over how much it went across by. So you can think of it as the change, and it's important that you understand it's the change in y, not just the y number, over change in x. So like let's say on here, that's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, and then that's 0 in the corner. So let's say we had this graph on this line. This is the line, and if I asked you, tell me what the gradient of that line is, you would figure out how much it went up by, so the change in y. One common mistake a lot of students make is just for change in y, they would write 7, but no, it didn't change by 7. It started off at 4, went up to 7, so the change in y is 3. The change in x is, once again, don't just write 6 because that's the last value. Find the change. 1, 2, 3, 4, 5. The change in x was 5. So the gradient would be equal to rise over run, change in y over change in x, 3 over 5. And you would just stick that into a calculator. I believe that is 0.6. Let's just check that. Hope I'm not being silly. Yes, that's 0.6. So the gradient is 0.6. And that would be the number that measures how steep it is. So it's got a steepness value of 0.6. Now let's apply that then to distance time graphs. When it comes to distance time graphs, we usually have on the x-axis time. So time goes on the x-axis and distance goes on the y-axis. So that's what a distance time graph is. Distance on y-axis, time on x-axis. And a lot of the questions that you're going to come across when it comes to distance time graphs is basically thinking about describe the motion of the object based off of what the graph looks like. So let's start on the left-hand side here. You'll notice that as time increases, as time goes up along the x-axis, so time going up along the x-axis, the distance isn't changing, right? It's not going up, it's not going down. The distance isn't changing, even though time is passing. So have a think about what this straight flat horizontal line represents in terms of the motion of the object. What is the object doing based off of the graph it makes? Well, because as time passes, distance isn't changing, meaning it's not going anywhere, meaning it is stationary. Still, not moving at all. So whenever you see like a flat horizontal line for a distance time graph, that means the object has stopped moving. Now let's look at other graph shapes for a distance time graph and analyze what the motion is going to be. So as time goes up, as time increases, We also do see distance increasing as time increases. But notice that it is a straight line, like a straight diagonal line. So as time goes up, distance goes up. As time goes up, distance goes up. And this is pretty much at like the same rate throughout because it's a straight line. So time going up, distance going up at the same rate. Think about this in terms of an object. It's covering distance over time at the same rate. This means that it's moving at a constant speed because it's covering distance over time. Every 2 seconds it covers 4 meters, and then that will like keep on going because it's a straight line. Now you'll see these are curved lines, which means that the speed isn't constant. So at the very start, our gradient is very, very small. It's not very steep at the start, and then it gets steeper and steeper. So let's analyze this again. As time increases, the distance is increasing, but not by the same amount each time. Like for example, at the start, as time passes, distance only went up just a tiny little bit, but then the same time passes and then distance goes up by a lot. So at the start, the object, you can think of it, was traveling really slow because as time passed, it only moved a little bit. But then later on in the journey, as time passed, it started moving quite a bit more. So we can think of it as speeding up. So the object is speeding up in this case when it makes a graph that looks like this, a curved graph that looks like this. We call speeding up as accelerating. Now let's do the opposite type graph to that. Time increases. Distance is also increasing because distance is also going up as time goes up. But you'll notice it starts to flatten out by here, our graph. So at the very start, as time increases, distance jumps up by quite a bit. But then later on, as time increases, distance jumps up by very, very little. So it's still moving because it's still covering distance over time, but it's covering less and less distance. So what does that mean then? Have a think about what that means. It's the opposite to this third graph by here. In this case, we have an object that is slowing down. We also call that as decelerating. Now what links all of this together is the gradient of our distance time graph. Let's look at the left-hand side on the very first graph we have. Change in y over change in x. Okay, x is changing, our time is changing, but did our value of y change at all? Did it go up at all? No, it did not, right? It stayed the same. So the change in y is 0, and with gradient being change in y over change in x, because its change in y is 0, that means then, in this case, the gradient is 0. With this though, there is a change in y, there is a change in x, and then we can use different positions as well. There is a change in y here, there is a change in x. And what I want you to notice is that a change in y, our y-axis is distance, Our change in x is our change in time. So our change in y is a distance. Our change in x axis is a time. What is distance over time? What value is distance over time? If you were here last lesson, you would know that distance over time is speed. So basically, from a distance time graph, you can actually calculate the speed using a distance time graph by calculating its gradient, by calculating its change in the y over its change in the x. Because the y, in our case of a distance time graph, is just distance. Our x, in the case of a distance time graph, is just time. So when you do change in y over change in x, you're basically doing distance divided by time, which is speed. So here we have an object that's moving at constant speed. Now with this, it's a bit hard to find a gradient. With these last two graphs, it's a bit hard to find the gradient because of the fact that it's not like a solid straight line. Because you'll notice that the gradient, the slope, the steepness is changing depending on where you're looking at the graph. Like for example, our slope here is a lot steeper, so it's going to have a higher gradient, higher speed than our bit of the graph by here where it's not very steep at all, so a low speed. So anytime you have steeper line, that means you are going faster because you're covering more distance over time. If you have a less steep line, that means you're going slower because you're covering less distance over time. Now let's put this into an example where we're going to analyze this graph. So this is a very common type of question where they would give you a graph that has loads of steps to it. But what I recommend for these types of questions is for you to break it down into each part of the journey. So, for example, anytime I see a change in the graph, that means that the motion has changed. Because all of the examples that we had like up here, all of the types on all of the shapes that we have, that is just the entirety of the graph. But you can combine all of these into one journey, right? Like for example, a car is stationary at first, so it would have a straight line, and then it starts moving, speeding up, and then it moves at constant speed, and then it starts slowing down. Stuff like that, where you would have like when you want to track a whole journey, you're gonna have a graph where parts of it changes, like this. So like here's a bit of the graph, and then you'll notice that because the graph changed, the motion's changed, then motion changed again, and again. The only reason why I'm labeling this is just for you to see all of the different sections of this graph. So let's break it down. What if a question asked, describe fully the journey of this car? Let's say this was a car. Describe fully the journey of this car. So, let's start with the first part of its journey. The first thing it did. In 10 seconds, it went 300 meters. So, our speed at this time, just get a different color. Our speed at this time, change in y is 300, change in x is 10. Our speed, remember, is calculating the gradient, so the change in y divided by the change in x. So our speed equals 300 over 10, which is 30. So in first 10 seconds, car traveled at a constant, because it's this like a smooth straight line, speed of 30 meters per second. Now let's look at the next bit, which is my section labeled B here. Notice that another 10 seconds has passed, right? Because the section of B goes from 10 seconds to 20 seconds. So another 10 seconds has passed, but you'll notice that the distance did not move from the 300 point. So it traveled to 300, a distance of 300, and then didn't go beyond that for 10 seconds. Now think about what that means. Remember what the shape of that flat horizontal line is? Then stationary, so not moving, for 10 seconds. Because it was started at 10 seconds and went on to second number 20, so it stopped moving for 10 seconds. Then it started going again, because now the distance has once again started increasing. Remember though, we want specifically change in y over change in x. So the change in y in this case, once again, do not just read the graph number and put that in for y. The change in y is specifically the change. So you're almost like drawing a little triangle here to work out the actual gradient of this bit only. So it started at 300 and went up to about 550. So that means that the change in y was 250. And the change in x was between 20 seconds and 40 seconds. So the change in x is 20. Then it started moving again at a speed of 250 divided by 20. That is going to be 12.5 meters per second. So then the car started moving again. Notice that at this point, our speed is a bit lower than the first speed we started off at. So in part A, its speed was 30, and then at part C, it was 12.5. And then notice what happened to the graph when our speed slowed down. The graph became less steep. The increase was less sharp. And then once again, we come across a flat straight line, horizontal line, where our distance isn't changing, even though our time is going up. So that's going to mean it stopped again. Then stopped for how long? It was between 40 and 60 seconds. So it stopped for a total of 20 seconds. And then finally, it started going up again, then started moving. Once again, make sure that you're doing specifically the change in y over the change in x. So the change in x was between 60 and 80. That means the change in x is 20. Our change in y is between 550 and 1100. So 1100 minus 550, that is 550. So our change in y was 550. Then started moving at a speed of, I'm calculating the gradient now, change in y over change in x divided by 20, 27.5. 27.5 meters per second. So I know that was quite a bit, but that was just to demonstrate that level of detail you need when describing these graphs, and how it's useful to break a journey down into multiple steps. So at the very start of this journey, it was traveling at a constant speed. We were able to calculate that constant speed by the change in y over the change in x, because remember, the gradient of these distance time graphs represents the speed, because speed is distance divided by time. Then we recognize that when the line goes flat and horizontal, that means that distance isn't changing at all, even though time is changing, which means that our object is stationary. Then it started going up again, and we have a gradient once more that we can calculate to calculate its speed at the time. Then it goes flat again to once again hint that it's stationary, and then starts moving again with another constant speed for you to calculate using the gradient. So the key mistakes a lot of students make, just so then you can avoid those mistakes, is when calculating for the gradient, they just take the number from the graph. Like for example, they would say for when calculating the gradient of part E, they would just write, okay, right, how much did part E go to? All right, 1,100, and then stick that in for Y, and then put over 80 because that's where the time stopped. So they would just put in single X and Y values, but nope, that's a mistake. You have to put in the change, not the actual value that you read from the graph. You have to put the change. I recommend drawing out these triangles just maybe at the start while you get used to this, in order to find that gradient. Find the change in y specifically and the change in x specifically, because you don't just want the number from the graph, you want the change in the number. Another mistake that a lot of students make is when it comes to the flat horizontal line, not recognizing that that means the object is no longer moving, which is a really important thing for you guys to memorize, and the trick to memorizing it is knowing and recognizing that distance is not changing even though time is. So it is staying still then, because there's been no increase in distance even though time has increased. Alright, now for a bit of practice. I'm going to link now some practice for you to do. It is on the website, but here you go. Instead, that's also a direct link. On the left-hand side, we have our worksheet with some questions. The second page, that was our graph that we just analyzed, but I want you to be able to read that graph and analyze and answer the questions on it. And then all of the answers to that worksheet are at the very bottom of on the right hand side, that PowerPoint. So we have all of the answers to those worksheet questions there for you. So distance time graphs, as a summary, the maths part is not that hard. All it is just calculating a slope by doing rise over run. So that bit is simple enough. But the hard part is taking the time to really sit down and analyze and think about what is going on here. What is the motion of the object going to be like? Is it moving? Is it not moving? How fast is it moving? How steep is the line? All of these things you have to consider when describing the motion of the object. And that's all to do with the gradient, knowing that the gradient is the speed. So have a go at a few of those questions. If you are looking at the answers and one of your answers doesn't match mine and you're not really sure why you're not getting it, feel free to send me an email, leave a comment, or leave me a comment on Show My Homework as well. Okay? Right, have a good rest of the day and enjoy your half-term break.